Welcome, everyone, and thank you so much for joining us here at our side event today on global monitoring of POPs with a focus on dioxin food chain contamination. For those of you who don't know me, my name is Therese Karlsson. I'm a science and technical advisor for IPEN, the International Pollutants Elimination Network, which is a global network of more than 600 civil society organizations in 130 countries. We're honored to be joined today by several speakers in the room and online, including several of the authors of a review on dioxins in the food chain that just got published last week. As you know, dioxins are some of the most toxic substances that are known, and the discussions that we will be having during PopRock this week are critical importance, since the brominated counterparts have been found to have the same concerns as the chlorinated counterparts. The draft risk profile clearly shows that these chemicals are persistent, bioaccumulate, have potential for long-range environmental transport, and are toxic and associated with a wide range of adverse health effects, including reproductive and developmental harm. The speakers today will provide more insights into sources, exposure pathways, and monitoring of dioxins. We will be moving rather quickly between presenters, and after all of the presentations, there will be time at the end for discussions and for you to share your insights as well. We will be starting with Dr. Roland Weber, who is a POPs environmental consultant with a long track record of researching POPs, including dioxins and furans. Roland will be speaking about his new review of brominated flame retardants and polybrominated dioxins and furans in eggs and contamination sources, which was just published last week in the Journal of Emerging Contaminants. Please go ahead, Roland.
Yes, good day, everybody. We got published our review, and actually it's not my review, it's actually, let's say, the work has been done mainly by IPEN. They gathered these eggs over the last 20 years, so therefore you see here many co-authors. But I helped them, let's say, to compile the data in a reasonable way to make it understandable. But actually, when you look back the last 20 years, free-range eggs are sensitive indicators for chlorinated dioxins and PCBs, contamination in soils, and eggs are also important exposure pathways from polluted soils to humans. Actually, the most sensitive exposure pathway from all pathways. So this we have shown in the review article in 2022, where we did the review for chlorinated dioxins and PCBs. So therefore, chickens and eggs are ideal active samplers and are also indicator species for soil contaminated with the brominated dioxins and furans, but also other POPs. So your work from IPEN goes back the last 20 years, where you sampled eggs around waste incinerators, metal industries, chemical industries, cement plants, e-waste recycling sites, dump sites, and other open burning sites. And when I looked in 2022 to these data, it was really striking, because from the 113 chicken flocks you have sampled around these sites, 88% of the pooled eggs were above the European maximum limit for chlorinated dioxins and the sum of dioxins and dioxin-like PCBs. This means close to 90% of these sites around metal smelters, incinerators, dump sites were contaminated in the soil, that the eggs basically were not to be recommended to eat. So at that time it was 113 chicken flocks. Today you have sampled more than 200 chicken flocks. And we just got published our review 2 weeks ago on the brominated dioxins and furans, and also brominated flame retardants in chicken eggs, including all data here which IPEN monitored, but also I did a review of the normal literature. That's all included. So the review was published here with open access, that also low-income countries have full access without any cost. So first, brominated dioxin in commercial eggs. There were a range of studies from Poland, Ireland, and Italy And these commercial eggs in these countries were quite low. They were somewhere between 0.15 picogram TEQ per gram up to 0.6 picogram. This means all of them were lower than the European limit of 2.5 picogram for the chlorinated dioxins. So this indicates mostly low levels in commercial eggs in these countries and a low exposure to PBDE through egg consumption there from commercial eggs. However, what was interesting was that higher levels of 21 picogram per gram fat for 2378 tetrabromo-dibenzofuran congener was detected in chicken eggs during a regular check in a national monitoring in Netherlands. So considering WHO recommendation, which said that the toxic equivalency factors for chlorinated dioxins should be used for brominated, this would correspond here the highest level to about 2.1 picogram TEQ per gram fat, which would just be lower than the European limit. But when we look to the bioassay to the 2378 tetrabromo-dibenzofuran, which is around 0.8, this means 8 times higher than the TEF of the chlorinated tetra, it would be 16.8 picogram TEQ. This means 6 times about the EU regulation, and this is normal commercial egg in the Netherlands. So in Netherlands, they said the poultry feed and feed additive measured in Netherlands contained these 2378 tetrabromo-dibenzofuran and was likely the source here for chicken and the chicken eggs. So therefore, chicken eggs containing brominated dioxins can contaminate commercial eggs at large scale, and the resulting brominated toxicity can be high, considering the actual dioxin-like toxicity from the bioassay. So here, IPEN also worked with this bioassay. They analyzed around 75 eggs, also with the bioassay. And here, they found that for several pooled eggs, the TEQ from this bioassay was considerably higher than could be explained from the toxicity of the measured chlorinated dioxins and dioxin-like PCBs. So therefore, IPEN additionally analyzed the brominated dioxins in these eggs which had unexplainable toxicity. So here, IPEN and Arnika were basically the first to measure brominated dioxins in a kind of systematic way of eggs collected near the pollution sources. So overall share here of brominated dioxins in the 43 pooled eggs, considering the toxic equivalency of the chlorinated dioxins for the brominated dioxins, we can estimate that 26 out of the 43 eggs, this means 60%, were above 2 picogram of brominated TEQ per gram fat. This is above the EU action level for chlorinated dioxins. And 24 eggs, this means 56% of the brominated TEQ was above the EU maximum level of the chlorinated dioxins. This means they would not be allowed on the European shelves or to sell. And these eggs cause that just 1 egg is enough to exceed the tolerable weekly intake for a child. So when we look to the individual sources for these 43 eggs, we see that the largest source and the highest contaminated eggs were at e-waste recycling sites. So here the highest egg was from Ghana, which had more than 500 picogram TEQ per gram fat of brominated dioxins. Additionally, this egg had also 850 picogram chlorinated dioxins. One of these eggs is enough for a child to have tolerable yearly intake, 1 egg. The second and third highest brominated TEQ were found in eggs also from e-waste dismantling sites in Thailand with more than 80 picogram and 30 picogram TEQ. And also another egg from Thailand had close to 20 picogram TEQ at a waste and e-waste sorting and recycling workshop where open burning regularly occurs. Also other eggs here from the Philippines, from Mexico, from Thailand, were all above between 6 and 14 picogram TEQ. This means more than 2 times above the EU maximum level and resulted in relevant dioxin exposure above tolerable intake, especially for children. Also, when we look to eggs around incinerators, high brominated levels were detected in pooled eggs close to a waste incinerator in Wuhan in China, had a 28 picogram TEQ, this means more than 10 times about regulatory limit in the EU, and here fly ash and bottom ash were disposed in the surrounding. Also in an egg at a lime kiln around Indonesia, there was an egg with 13 picogram TEQ. 75% of the total TEQ came here from the brominated dioxins and only 25% in addition to the 13 picogram from the chlorinated. Also in the Philippines, and there was a detection with 1.5 picogram brominated dioxins, so this is close to the EU action level of 1.75 picogram, and the action level mean that normally it need to further be evaluated what is the source for it. So therefore ash residues from incinerator, especially the bottom ash, can be contaminated with brominated dioxins and also PBDEs, especially if the bottom ash had a bad burnout of grade shiftings are combined with the bottom ash. So if the incinerator is not good, then the bottom ash is not good. Yeah? And therefore you do not get all the plastic particles really burned. Yeah? So therefore it can go into the ash. But there is also for BAT incinerator one problem. When you have a grade incinerator, which are, let's say, the most used incinerators, you always have grade shiftings. This means some % of the waste is falling through the grade. Yeah? And this is not subjected even in a BAT incinerator. And then it depends what you are doing with the grade shiftings. Normally you have to reintroduce it to the incinerator and burn it again. But if you this is the easiest, is just to combine it with the bottom ash. Yeah? So, and I think that this is one reason that we find here in China, but also in Europe, when we look to the grade shiftings, brominated dioxins there. So for non-BAT incinerators, also we have to look to stack emissions. So we know that also brominated dioxins can go through the stack if the incineration is not good enough. And I think what is quite interesting in future and currently is that pyrolysis plants are increasingly treating plastics. You know, with all the chemical recycling in all the countries, it's pushed for it. But when you have these brominated flame retardants and PVC in these plastics partly, then you get a problem with brominated and also with chlorinated dioxins there. Coming to assessments around landfills and dump sites. So here we know from the US EPA that open burning from dump sites can really emit high emissions of brominated dioxins. Here Gallet et al. From EPA found 417 nanogram TEQ per kilogram carbon burned of emissions of brominated dioxins. This was a dump site in Mexico. So here IPEN measured 5 pooled eggs in Nairobi, in Tanzania, in Gabon, and all of these eggs were above, up to 14.4 picogram TEQ, and also the chicken egg around in the Uruguay landfill was at 1.7 picogram TEQ. This means also 10 times higher than the European commercial eggs. Yeah, and also in Yaoundé, in Cameroon, it was 1.5 picogram TEQ per gram fed. So you see, not as high as e-waste sites, yeah, because much of the waste is normal plastic waste, which does not have, let's say, brominated flame retardants. And also in this egg in Cameroon, the levels of PBDE were very low, yeah, 2.7 picogram, nanogram per gram in the egg. Yeah, so you see that landfill does not have much of the PBDEs. Also around metal industries, they sampled. So here we know that brominated dioxins can be elevated in secondary metal industry. So here IPEN had four pooled eggs in different areas measured. And in Indonesia, it was 2.9 picogram TEQ. In Georgia, one of the egg around the metal plant had 11 picogram, but in the same area, IPEN measured 2 other eggs, and the 2 other eggs were low. This means here it was not the metal industry actually. And when we look here into the PBDE pattern in the egg of Georgia with the high dioxin level, it had 96% DKBDE and only close to 4% non-BDE. This means we have a complete commercial DKBDE pattern. And from a metal smelter, we would not expect that the emission is a pure DKBDE because you have depromination in the metal smelter. So what I concluded here in the review is that this chicken did pick just a plastic particle containing DKBDE and some of these brominated dioxins. And also in the other metal industries, I think in total IPEN monitored more than 20 metal industry, we did not find really, let's say, bio-TEQ much above the chlorinated and the PCBs. So there, for metal industries, the driving force are the chlorinated dioxins and the PCBs. Coming to shredder plants, we know from a good Australian study that PBDEs around the shredder plant is elevated. And here, unfortunately, IPEN only had one egg from around a shredder plant that's from Mexico. So this egg contains 6.2 picogram TEQ of brominated dioxins, more than 2 times above EU limits, and 230 nanogram of PBDEs. So this indicates that contamination here from the environmental surrounding of this shredder plant treating electronic waste. General discussing of major sources. So in my opinion, the main global source for brominated dioxin in plastic are the 2 million tons of PBDEs. Yeah, we had done a study 10 years back in Nigeria. We have analyzed individual cathode ray tubes, and we did a correlation between the brominated dioxins and the PBDEs. And we had around 0.1% of brominated dioxins compared to the PBDEs. When you take these 0.1% roughly in products and you multiply it with the 2 million tons, so we concluded at that time that we have around 1,000 tons of mainly PBDFs as unintentional co-pollutants, considering the ratio here from our study. But this 1,000 ton is not the TEQ, this is the total amount. That this driving dominance of PBDEs for brominated dioxins in plastic can also be seen from recycled plastics. So this is a study from IPEN where they analyzed from plastic toys globally 48 recycled plastic samples. And what you see here in gray, this is octa-BDF. And in blue, this is hepta-BDF. So you see 97% of all the brominated dioxins in the recycled plastic is a pure DKBDE pattern. Yeah? In total, they had only in one sample, there was 10% of brominated dioxins, but also here, let's say, the higher ones. When we look now to the pattern in the eggs, yeah, and that was for me a headache for a week to think about it, and the source, you see also, let's say, the blue one, this is octafuran. The light green one is the heptafuran, yeah? And the light yellow one, which is big on the left side, this is octadioxins, yeah? So my interpretation is that 2/3 of the samples which contain high octabromodibenzofurans, high heptadibenzofurans, and octabromo dominated the total dioxin pattern, that this comes from the commercial DKBDE. However, what we see there is that the contribution of the heptafuran is considerably higher compared to the technical mixture. So therefore, here we see really this thermal depromination from the DK, also then in the dioxins, that we have a higher contribution from hepta, from depromination. And this happens always when you heat the DK together with plastic, and there you have also the antimony trioxide, so, which help to deprominate. A second observation is the relatively high share of PBDEs, in particular octabromodibenzodioxin and heptabromodibenzodioxins. So normally we have only the furans, right? You saw the plastic before, yeah? In thermal processes, when you have high content of metals, you can also transfer to the dioxins, yeah? So when you have ashes with high metals, you can form the brominated dioxins. In my opinion, this is a part of the explanation. I think that a second factor might be the formation of brominated dioxins from degradation of DKBDE in the chicken, yeah? And this is really something for research, yeah? I have already contacted some friends in Japan to have a look at some samples, because when chicken metabolize DKBDE, they do a hydroxylation, yeah? And I think that this is a reason for it. Then you look to the red ones. The red one is the 2,3,7,8 tetrabromodibenzofurans. So this we have also in many eggs, and it is consistently present. And in my opinion, the source is most likely the thermal degradation of tetrabromobisphenol A, which result in the formation of largely dibromofurans, tribromofurans, and tetrabromofurans, including the 2,3,7,8 tetrabromodibenzofuran. Yeah, so this is from Ortuno et al. You can look to the patterns. Therefore, we consider that the DKBDE and the tetrabromobisphenol A were the main precursors for brominated dioxins in the egg. So also there are other brominated flame retardants which contain brominated dioxins, but also which have the formation potential, like for example the 2,4,6 tetrabromophenol. But the level of this are much, much lower than the tetrabromobisphenol A. Yeah, they also have a good dioxin formation potential, yeah, but the levels in the products and so on, the tetrabromobisphenol A is by far the biggest. So therefore, yes, we have an overview here for exposure pathways. Let's say all these sources which I showed are contaminated soils and then contaminated chicken egg, but also we see from Netherlands, yeah, that you have this fish feed, for example, yeah, and some others which contain this tetra, which are exposure, or it can come from bedding, where we need to take care when we go to recycling circular economies. And also we have the point sources, of course, at farms, where chicken can pick some of these, for example, the EPS, XPS is here a big problem. So in our review, it's not only brominated dioxins, I also have there the brominated flame retardants, where you see that sometimes chicken have very high levels of hexabromocyclododecan in the eggs. Conclusions and recommendations. Environmental pollution by brominated flame retardants and related brominated dioxins and furans. Contamination can occur along the life cycle of brominated flame retardants, from production, use, in production, use and storage of brominated flame retardant treated products, and in particular, in the end of life, with frequent open burning of waste, particularly in low and middle income countries. So the second part of the sentence, this comes from the study as a proof. The first part of the sentence, this is just the experience that always when you produce these chemicals and when you use it in production, you also have the release. And there are good studies from Japan about the emissions of the use of PBDEs, for example, when you use it in the production of electronics. Sites where e-waste end-of-life vehicles are recycled involving open burning can be contaminated by brominated dioxins, mixed halogenated dioxins and chlorinated dioxins and plastic additives, and can contaminate chicken eggs far above the tolerable daily intake, even that high that one egg is enough for 1 year for a child. Therefore, chicken and other livestock, of course, should not be raised on these areas. Ash residues from incinerators, especially the bottom ash, can be contaminated with brominated dioxins, but also PBDs and PAHs. So here, bottom ash is recycled in a range of countries. It's a huge volume, yeah, and is often going directly into landscaping, yeah. So here, this need to be taken care. And maybe we know we need low pop content limits or unintentional trace contaminant limits for bottom ashes. And also here the grade shiftings in stocker incinerators should not be combined with the bottom ash, but should be reintroduced. Drivers for the brominated dioxin formation and exposure are PBDEs as direct precursor and other aromatic brominated flame retardants from forming brominated dioxins in thermal processes, in particular the tetrabromobisphenol A, due to his high volume in that waste. Specific TEF values for brominated dioxin should be established, especially for the 2,3,7,8 TBDF, known for its high dioxin-like toxicity in bioassays. This is close to the tetrachlorobenzodioxin, which is currently quantified just with the low TEF of 0.1 of TCDF. This is relevant as you have seen, the TBDF is also frequently detected in the eggs, but also for the Netherlands was in the feed and in the normal commercial eggs. The pyrolysis, including chemical recycling of plastics, is increasing, and is known that pyrolysis of BFR and PVC containing plastic from e-waste and end-of-life vehicles can form and emit chlorinated, brominated and brominated chlorinated dioxins. I have written one of the first studies in 2002 on this pyrolysis when I was in Japan in my company. However, there is a lack of assessment, and it is recommended to monitor releases and pollution around operating plants and increasing operating plants, and also the resulting products like pyrolysis oil and carbon black from chemical recycling. Strict limits for POPs content in waste should be introduced into national legislation to regulate disposal and recycling options and prevent contamination of the environment and food. Also, recycling of waste and the disposal leading to further spread of POP BFRs and brominated dioxins should be stopped, and taking care of all your e-waste and generally brominated flame retardant waste. Therefore, listing of brominated dioxins and furans and mixed halogenated dioxins and furans in the Stockholm Convention would address these substances globally and synergize with the existing treaty obligations related to POP BFRs and the chlorinated dioxins. And the listing of brominated dioxins and mixed halogenated dioxins in Annex C under Stockholm Convention could and should trigger then an adaptation of the Annex C BAT-BEP technical guidance. And in my opinion, this should better consider the monitoring with dioxin bioassays, because this is currently the only practical way to cover at a reasonable cost chlorinated dioxins, brominated dioxins, and particular brominated chlorinated dioxins. We have 5,000 congeners with the mixed halogenated dioxins, and 1,000 of them are 2378 substituted. So at the moment and in near future, it will not be possible to analyze them with instrumental analysis. Yeah? But with one bioassay, you can cover the whole dioxin-like toxicity. Also financeable in low-income countries, and by this I will hand over to my next speaker. Yeah? Thank you for your attention.
Thank you very much for that, Roland. I'm very happy that this review was published in time for this year's meeting.
That was stress.
I can imagine. I find it especially concerning, if I understood you correct, that samples show that just one egg would have such high concentrations that it would correspond to 1 year's tolerable intake.
Yes, that was at this Ghana site. This means these are really sites which are long years contaminated. So the soils are highly contaminated with chlorinated, brominated and mixed halogenated dioxins. This is, for example, in Akprokoshi, but we have the same in Guyu in China. Actually, I analyzed in 2008, we analyzed in the Swiss laboratory samples from Guyu, and they were even higher than the samples from Akprokoshi. So this means this long year burning, open burning, just adds up to this dioxin contamination in the soils. And this happens now in many countries, where they recover the copper cables and let's say all these metals from this informal recycling. Yeah.
That is incredibly concerning. Next, we will hear from Lamine Jaite, who is a program officer at the Chemicals and Pesticides Department of the National Environmental Agency in the Gambia. Lamine is also a current POPROC member and will be speaking about the importance and challenge of monitoring dioxins in African countries. Thank you so much for joining us here, Lamine.
No, it's okay. Thank you very much, Teresa. Thank you very much, IPEN and Arnika, for inviting me to join in this side event. Basically, my presentation will be a very short presentation. It's basically to talk about the importance and some of the challenges that we face in monitoring POPs in Africa. I could easily speak about this because I am currently updating the NIP, and I've worked on the NIP previously. And we find it very difficult in most cases to be able to get quantitative data analytically to actually quantify the amount of POPs that we come across. So, like she said, I'm a registrar for pesticides and hazardous chemicals and also a POPROC member. So, just a quick overview of UPOPs, dioxins, specifically these are compounds that are actually referred to as dioxins, and they are detected in all environmental compartments in trace amounts. This is a common knowledge for everybody. They are unintentionally produced. Currently, we have 7 of those that are listed under the Stockholm Convention: HCB, HCBD, pentachlorobenzene, PCBs, and dioxins and furans, chlorinated ones, and then the polychlorinated naphthalenes. So to look at them, Roland has actually talked about the most toxic one that a lot of concentration is given to. That is the 2378 tetrachlorodibenzo-P dioxins, and they are classified as human carcinogens. This is actually done by IARC. Other than that, the usual exposures, human exposures, are mainly occupational exposure or accidents. And in many places, for example, in developing countries, through secondary exposures, through dietary intake, like eggs, milks, and then we will give some presentation, some literatures that have actually measured dioxins through dietary intake. So some of the primary sources, I don't know whether it's well visible here, for dioxins and furans. People that work most of the time in Pop Rock are familiar with this, particularly municipality waste incineration. This is a common source. For example, in the Gambia, in my own country, 98% of most of the sources are coming from open burning of waste. Roland was in my country, and he can attest to that. Cement kilns are also sources. Limestone production is also a common source from the transport sector. Iron core production, coke production is also a common source of dioxins in many developing countries like the Gambia. So also in the transport sector and also power generation, because we still rely a lot on heavy fuel for power generation, and this is where most of the dioxins are also coming from. So in the informal sectors, for example, in textile production, leather plants are also common sources. Crematoriums are not very common in my country. We don't have a crematorium, but in some countries within the region actually use it. Landfills are also common in so many countries within the region. So talking about some of the sources, I will give some classical examples from my own country. Foundry work, this is still done a lot. For using aluminum to develop, to produce, cooking pots. They are still common in the informal sector. Open burning of waste. There is a huge amount of, landfills in so many countries, in developing countries, and also open dumping areas where the waste are usually burned. And a significant amount of the waste are not being segregated. They contain plastics and all other kinds of materials, electronic materials, polyurethane foams coming from old refrigerators that are imported into the region. A lot of second-hand materials are imported, and most of them cannot be used anymore in the region. So they end up in the dump sites where they're actually burned for metal reclamation. Also, fish smoking is also a common activity, particularly in my country, where a lot of people do fish smoking and curing, because fishing is the third largest source of income. So people smoke a lot of fish in these informal sectors where they have very kind of an oven-like. They use all kinds of materials, sometimes old cartons, even plastic materials, or even wood to actually smoke the fish. So the other one that you're seeing is for animal carcass. A lot of people use it, animal skin for their soup. It's actually put inside the soup, but it undergoes a lot of burning to remove the top surface. And in some informal sectors, you can find people using all kinds of materials to actually get this thing done, even though it's not acceptable in the country. So charcoal production, this is done a lot in the informal sector. Charcoal is still used in my country a lot as a biofuel for cooking. So when they do this, they usually put together a huge amount of plant biomass together, and then they will put them in a form of a heap, and then they will light fire within. So it will burn in a slow process. So while it does these things, smokes are actually released. This is a incomplete combustion, because when you completely burn the wood, you will not be able to have charcoal. This is a common activity in my country as well. So limestone production is also still done, where most of the limestone that is produced is used in the house for decoration or painting. So metal reclamation, I had Weber talked about this. This is a very common activity, particularly from car tires or even wires where people reclaim copper. This is sometimes done in the open and is very common in so many countries also close to my country. In some countries, it is not very common. They have big dump sites where people put together a huge amount of electronics to be able to reclaim precious metals for use. So these are some of the sources that we were able to find in our NIP. So this is just talking about Article 5 of the Stockholm Conventions, where the requirements to identify and characterize and quantify and prioritize the releases of UPOPs. So talking about this, then I go into the core of my discussion, which is to talk about the importance of monitoring dioxins and related halogenated POPs in our environment. So this is important actually to minimize and also where possible to prevent exposures to POPs, to humans, wildlife and the environment. I think this is the primary objective of the Stockholm Convention and why we are here to list and to look for new chemicals. It is important also to have an understanding. It helps us to have an understanding of the fate and the behavior of POPs in the environment. In most of our risk profiles, talks about the fate of these chemicals in the environment, and which is very complex in many sense. So it assists us to do a proper risk assessment, because a huge amount of industrial chemicals, even in the EU, have a complete risk assessment. So mostly pesticides that are used, plant protection products are more comprehensive in that sense, and also for policy development. So also it's important to meet our international obligations, like in the Stockholm Convention, our reporting obligations. We can only report if we find information. So if you look at a lot of NIPs that are coming from developing countries or least developing countries, their quantitative information on POPs is usually very, very limited. So therefore, monitoring information helps us a lot to be able to input these informations in our NIPs. Public awareness is important as well, because when you want to sensitize people about POPs, possible sources of POPs, you need to have quantitative information to give them so that they can understand the realities rather than just qualitative information or descriptive information. It's also important for trend analysis. We saw this in the morning when we had the informal meeting, trend analysis, to be able to know how much of exposures have been recorded over the year. This helps us in our decision makings and also in our policy developments as well. So I picked up some classical examples from literature's exposures in the region. Weber talked about, Agbolesia in Ghana, a publication that was done by IPEN and Arnika that looks at 3 cities in Africa, Ghana, Kumasi, and also in Yaoundé. Agbolesia is considered as one of the largest, scrap metal yards or e-waste yards in the world, where a huge amount of people rely on daily. About 40,000 inhabitants within the region, and over 80,000 people rely on this site for daily activities. So what they did in the research is they looked at fringe-range chicken eggs, soil samples, and ashes close to the waste, the scrap e-waste site, and also look at medical incinerators and also waste incinerators. Samples were collected. And if you look at the results of the analysis for the eggs, and also they took a reference background sample, which is egg from supermarkets, and they were able to test, chlorinated dioxins and furans at concentrations of about 661. That's quite a significant amount compared to the maximum limit of the EU, which is a 2.5 for eggs. They also looked at some soil samples with concentrations as far as 4,524. This was just mentioned by Weber due to the years and years of accumulation of these dioxins in the soils. So it is obvious that you can find such high concentrations in the soils. So 3 out of the 4 free egg chicken samples exceeded the EU limit values from this study, with highest levels of dioxins at 661 picogram WHO TEQ per grams fat. This is above the EU maximum limit of 2.5. This is a significant amount from their studies. I also looked at another study that was done in 2022 that was looking at polybrominated flame retardants and also dioxins from 11 African countries, from plastic materials, recycled black plastic materials, to be able to check how much of brominated dioxins are detected. So in most of this, it was African countries and some Arab countries. So I was able to highlight some. The highest from South America that was detected was like 14,100 picograms per toxic equivalence per gram. This is a significant amount. So in Kenya, they had about 6,591 from this plastic that have been tested for brominated flame retardants. And about Gabon, they had about 1,430. This is also a significant amount. So Nigeria, from Rubikut, they had about 56 picograms, which is also still high. So you have about 8,118 from Jordan, from the comparative analysis. So going further, I was able to see also another study that looked at polychlorinated dioxins and furans, and dioxin-like PCBs and the non-dioxin-like PCBs that have been tested from serum from about a significant amount of 693 individuals from South Africa. So they've also looked at people that are using bone, solid biofuels, and those that are using electricity, gas, and paraffins as their source of fuel for cooking. And a significant amount concentrations were found in those that are actually using biofuel for cooking. So to conclude, I will look at some of the common challenges, like Weber says, in most of the countries within our region. First is limitation in instrumentation capacities. We've seen that a lot of new POPs that are coming in are very complex to analyze. It would require a high level of instrumentation. From personal point of view, I had samples that I wanted to analyze for PCBs. We did rapid tests in the field for PCB transformers, oils, and soils. The quick test can give you some false negatives and positives. So out of more than 100 that were tested positive, we sent them to Switzerland, and then out of only 8 came out to become actually positive for PCBs. I also had a similar situation where I collected samples from a river very close to a sludge wastewater treatment facility. So to get these samples to Sweden was a problem because I needed to freeze them. So when I even went to the couriers for them to export it to Sweden, a lot of them were saying no, that they don't transport liquid samples. So I had to do some sample preparation, filter them, put them in kind of a small filters like this, freeze them, and then put them in a cooler, and then try to travel with them. I still have them in my lab. So this is one of the challenges. So sampling also is a problem because some of the terrains are very difficult to get access to. Some of the sample matrices can be very, very, very complex, and some of them will require a rapid testing. So analytical infrastructure, like I said, for example, when you have a GCMS, I have one in my laboratory, reagents are expensive, reference standards are expensive. It's difficult to even motivate, the decision makers for fundings to be able to do most of this analysis. This is also a problem for us. High cost of maintenance. If, like in the Gambia, the closest Agilent agent will either be in Egypt or will be in Abidjan to get them to come and do some basic maintenance work when your instrument has an issue. So imagine POPs, some of them are becoming very complex to analyze, and I think a lot of you can attest to that. So limitation also in POP knowledge also is one of the constraints that we have in the region to be able to effectively monitor POPs in the environment. So basically, I think this is what I have, and thank you very much for your attention. Thank you.
Thank you for sharing your insights, both from the work on NIPS and from practical sampling. I think that's very valuable for the discussions that we will have this week, also for the discussions on traceability. I also want to highlight that both you and Roland have been talking about these recycled plastics, which I think is very important to note, given that this creates yet another pathway for both exposure and potential long-range transport. So thank you for sharing your data and experiences. Our next speaker will be joining us online. Titikorn Bondongmai works as a program officer for Earth Thailand, which is a non-governmental organization that works closely with communities that are affected by waste management, illegal dumping, waste trade, and hazardous waste recycling. He will be sharing experiences with dioxin contamination at e-waste dismantling sites in Thailand. I hope you are with us online.
Yes, hi. Hi. Hope you hear me. Can you hear me? Okay. Okay. I just share my screen. Okay, this work. Hi everyone. Good afternoon, everyone. Thank you, Teresa, and thank you, Anika and IPEN, to invite me to this side event. Today I come to share about the POPs study in Thailand. Examining the dioxin contamination in environment, food chain, and human health in the surrounding of electronic waste recycling site in Thailand. Okay, this for the first, this the code you can scan here for the full report. For the 2021 to 2022, the study by Anika and Earth Thailand had collected the 61 sample of environmental and the food stuff and bus sample from the number of the local adult e-waste recycling workers in the Glasin, the northeast of the Thailand. We collect the sample at the various stages. The first is the dismantling of e-waste in the workshop. Second is sorting and gliding of waste plastic in shredding workshops, and transportation of non-utilizable leftover to the dump site to be burned. And the last one is the bottom ash from the dump site brought back to the workshop and processed again. All of the sample collected, the total of the sample is 137 samples, including the 61 environmental sample from the e-waste processing, compared with the 10 sample from the reference site, and the 40 human blood serum sample from the e-waste worker, and 26 human blood serum sample from the reference groups. The environmental sample include the dust, soil, sediment, bottom ash, with like a shredding plastic piece or some other plastics shredding, and the rice grains, fish, snail, crab, eggs from the free range chicken eggs, and the brachylium from the workers and the reference group. Okay, this show the gradient sampling around the dam site. The area for taking environmental and food sample were conducted at the dam site and its surrounding in the rice field. From the picture, you can see the dam site in the center, and around the dam site is the rice field. And next, this environmental sample will conduct in the village. This is the home and small enterprise currently or formerly involved in the e-waste dismantling and the sorting plastic trading enterprise. From the picture, you can see the boat area, living area, and the working area are really close. Yes, it's really close, and some of this place is the same areas. And according to business owner or the business operators, most of the hazardous waste and e-waste originates from auction yard and major cargo ports from the eastern of Thailand, but is it illegal? Yes, the picture show the all of the dam site in this study area. This is the municipal waste dump site is completely turned to be the e-waste dumping ground. All of it is e-waste. And some of these sometimes they open burn it in the dump site to fire or sorting some the metal, the copper, or some other. And these are the fuel and chickens in the workshop and household areas. For the reference area, we took the sample from the organic farm with no e-waste activity, and the blood sample collected from the farmer working or living in the village. Yes, and for the control aids, we bought from the supermarkets in the town area. And for the blood sample, we collecting the blood sample and the questionnaire. For the result, we found very high level of the dioxin of the bulbs, like a PBDE or some dioxins and furans. And these chlorinated dioxin, furan, and dioxin, like PCB, we found in the environmental sample and foodstuff. The dead sediment and dust and the bottom ash will find very high level of the dioxins. From the picture, from the chart, you can see the sediment is very high level, 1,400 picogram take per gram dye weight. It's very high than the it's very higher than the reference area of about 1,000 tons. And for the foodstuff, we found very high levels of the dioxin, like in the eggs, fish, rice, and some the apple snails. This graph compare the chlorinated dioxin and furans in the eggs in various study areas. We found the high level of the dioxin furan in the example. It's quite high, similar to the level found in the previous study conducted in Thailand in 2015. Yes, the red square. Yes. And next, we found the brominated dioxin and furan in the study found in the environmental sample and foodstuff mostly higher than the reference area, like a sediment, bottom ash, the dust, the aquatic sample, the eggs. Yes. And the study found the dioxin furan in environment and French chicken eggs higher than the control area and the previous study in Thailand. Yes. And for the PBDE, we found in the blood sample of the workers at 19.9 nanogram per gram lipid, higher than the reference site up to three times. And it found a PBDE in the number of the experimental sample tools. From the picture from the chart, you can see all of the PBDE in the study areas. It is quite higher than the control area in any samples, like a fish samples, apple snail, ash, sediment, dust, soil, eggs from the brain chickens, and the blood serum. Yes. And for the PBDE in the eggs, we found PBDE in eggs around 200 to 250 nanogram per gram of fat. Not higher than in some country, but the contamination level are still high and can be dangerous if exposure to this substance occur in the human body. Yes, and for the conclusion of our study, a wide presence of most of the study chemicals in the environment as well as in e-waste workers themselves was confirmed. The foul POPs contamination of this community can be linked to waste and e-waste recycling activities because the level of environmental sample and blood sample from the study area in comparison with the reference site considerably higher than PCDD FS or polyethylene dioxin furan and the dioxin lipase PCB and the other substance, the POP substance. Yes, and there is a substantial difference between the concentration of PBDEs and declaimers in blood serum. Yes, and the contamination by PCDD and dioxin and furan and the dioxin PCB and other substance of the POPs were highest at the dump site. The concentration of the pollutants decreased according to the distance from dump sites. For concentration of all of the dioxin in the dust sample were generally higher in the e-waste working area than cooking and living area of the household. Our study underscore and the facts that developing countries such as Thailand are already being seriously affected by these POPs and dioxins. We have found clear evidence of the contamination not only within the food chain but also in the blood sample of workers who were directly exposed. This situation raised grave concern for both environmental integrity and human health, and demonstrate the urgent need for stronger global action. Okay, that is. Thank you for your attention.
Thank you very much for Vikorn for joining us online and for all your work on these samples. The images that you share are very illustrative of how it works on the ground. I also want to thank the Secretariat for all their help, but especially for making it possible to include online speakers for this event. It's very valuable. We're running a bit short on time, so we'll be moving swiftly to our last speaker, which is Dr. Jindrik Petrlik, who is the head of the Toxic and Waste Program at Arnika and co-chair of the IPEN Dioxin Working Group. He will be talking about how waste incineration residues are underestimated sources of dioxins. Please go ahead, Jindrik.
Thank you, Therese. As Therese mentioned, I work as an expert for IPEN on dioxin and waste. As such, we focused on looking at the dioxin levels in waste incineration residues. In 2017, we published this report, which tried to follow dioxin levels and other POPs levels in fly ash from waste incineration. Unfortunately, going through scientific literature, we found out that waste incineration fly ash is used for building roads and sidewalks. This is a picture from my home country, Czech Republic, and we found that it is also suggested to be used, or it is used for construction products such as cement or bricks. It's used as a cover layer at municipal landfills, but also it is used, or at least suggested to be used, for embankments. And what was most strange finding that some scientific studies suggest to use the waste incineration fly ash also as amendment to soil in agriculture. This is a picture from Norway. This is a place where most of fly ash from Swedish incinerators is deposited in a limestone quarry on the island of Langøya near Oslo. We found also this scientific study which looked at the levels of contamination by heavy metals, but also dioxin near marine landfill of waste incineration fly ash in Bermuda, where the blocks made of fly ash were used as an artificial basis for coral reefs, but in fact it leads to contamination of the coral reefs rather than it helped. When we look at one of the examples in Thailand, in Phuket waste incinerator, we found out that both bottom ash and fly ash were stored in mangrove area next to waste incinerators. So we collected samples of various seafood, and there were several studies looking at the levels of dioxin in both bottom ash and fly ash. One of the oldest was in Thailand dioxin sampling and analysis program, and found the levels of chlorinated dioxin between 0.65 till 3.10 nanograms TEQ per cubic meter in air emissions, but also significant levels in fly ash. And in general, there were found levels in bottom ash and fly ash between 8 till 8,000 picograms TEQ per gram throughout the years where it was sampled. Last sampling was done by Arnika in 2022, and we found levels up to 770 picograms TEQ per gram dry meter of chlorinated dioxins, and it is summarized in this study. We looked at various sites where the fly ash is not handled properly, and we tried to follow what levels we can find in food chain, specifically in free-range chicken eggs, which were major topic of reviews presented here by Roland. So I will not talk too much into details, but this is a table from one of our studies published or presented at the Dioxin conference, where we compare the levels in fly ash and in nearby areas of soil sediment and in the eggs. You can see that a contamination of such areas can lead up to 20 times higher levels in the eggs for chlorinated dioxins than is EU limit value, and much higher levels comparing to reference sites. One of the sites presented there is quite known example from UK, which is Newcastle case from 2000, where the waste incineration residues were used for pass between allotments, but less known is this area in Bishop's Cleeve, where the waste incineration fly ash is handled, and we found high levels of dioxin in the eggs in nearby area. Another example is from Ghana, very close to Agbogbloshie. You can find this abandoned medical waste incinerator and also waste incineration residues, where the hens walk and feed. So we found high levels, 20 times higher than the EU limit value for dioxin in free-range chicken eggs from that area. After finding all these data, we tried to look at the total amount of dioxin, which is in fact suggested to be left without control, because low POPs content level for chlorinated dioxins is quite flexible. And when we looked at the levels of chlorinated dioxins in fly ash, we found out that if we counted for all waste incineration capacity on Earth, we come to total amount which is equal to tolerable daily intake of dioxin for 133 populations of Earth. Fortunately, not all these dioxins get into our food chain, but anyway, even a very small amount of this volume is very worrying. You can find more details about this calculation and a study in our abstract for Dioxin conference, and which is available on ResearchGate. And now I come to brominated dioxins. Roland, they are, what is interesting is that the brominated dioxins are in higher levels and high amounts in bottom ash from waste incineration, which was demonstrated in this study from 2010. So you can see that total mass of brominated dioxins in bottom ash is higher comparing to fly ash, and also comparing to air emissions from waste incinerator. And taking that into account, I think we should be aware that a lot of bottom ash from waste incinerators is used for construction, as construction material. These pictures are from Katwijk in Netherlands, where bottom ash is used for building roads widely. When we come to the food chain contamination with brominated dioxins, we already talked here about the review of brominated dioxin and furan levels found in free-range chicken eggs. This is a graph from our study, and these are the examples of levels of brominated dioxins which relate to the ash residues, not only waste incineration, like, for example, from China, Wuhan, but also from metallurgical industry or from some kind of semi-waste incineration, like in some cases. This is the ash from e-waste site presented by previous speaker, and you can see that the highest level found in free-range chicken eggs was from the house where chicken had access directly to the ash brought from dump site where e-waste was burned. In Indonesia, we found high levels of brominated dioxins at the sites where ash from burning of plastic waste or ash from metallurgical smelters, small smelters, were used and were accessible to free-range hens. This is the example of Wuhan waste incinerator in China mentioned by Roland, and you can see that there was a higher level of brominated dioxins found comparing to chlorinated ones. And this is most likely reason for such a high level, because the fly ash was stored openly in the area of waste incinerator next to the site which we sampled. You can find much more detailed cases and more information in the recent study which we have done with other colleagues from Arnika and IPEN. You can find this study focused on waste incineration in broader scope on our ResearchGate. Thank you for your attention.